Before we get into it, I want to set the tone. In this video, I'm assuming that if you are an engineer watching this, then you are probably experienced. You've seen watchdogs, brownouts, and resets before. This won't be a reteaching of fundamentals. This isn't a tutorial. It's not a teardown, and it's not a step-by-step guide. What I'm sharing here is something slower, space to think about how we build systems, and sometimes how they fail. If you work with embedded tech, or design for healthcare, or just find yourself wondering how we could do things differently, I think you'll feel at home here. And if you are here for a quick how to, or a parts list, or a rehash of fundamentals, that's totally fine. There are plenty of great videos out there for that, just not this one. So, with that said, let's begin. Most embedded systems can crash and recover. Your smartwatch, your router, even your car. The system hits a fault, maybe a buffer overflows, a watchdog kicks in, and it reboots. No big deal. But some systems don't get that luxury. Take a pacemaker. It's buried under your skin. It keeps your heart beating on time. If it stops, even for 1 second, the body doesn't wait. There is no pause, no error message, no time to restart. In embedded design, we lean on recovery. Watchdogs, brownout detection, reset pins, safe defaults. We plan for failure and we plan to bounce back. But what if bouncing back isn't good enough? What if the act of rebooting is the failure? A pacemaker rebooting means losing state. It means losing rhythm, timing, context, maybe even trust. Because when that reboot happens, the heart keeps going. It doesn't wait for your scheduler to restart. The heart doesn't say, sure, I'll hold off for a few cycles. So, what do we do when a reboot isn't safe? We design so the system doesn't need to recover, it needs to avoid failure in the first place. And if something does go wrong, it needs to keep working through the fault. That's why critical systems focus on prevention over recovery. We talk about redundancy, duplicate sensors, circuits, and logic paths. Pacemakers rely on a single long lasting battery designed to operate reliably for years, sometimes a decade or more. When that battery depletes, the entire device is replaced. We build in segmentation, keeping the core pacing logic separate from everything else. Logging fails? Fine. Data syncing lags? Acceptable. But the pacing loop that stays untouched. Watchdogs are still there, but the goal is simple. Never let them fire. Even power management is layered. Soft thresholds, regulated draw, monitoring systems that warn long before a dangerous drop, all designed not to trigger a reset, but to prevent one from ever happening. Glitches, we counter them with overvoltage protection and soft start circuits. In these systems, a fault may occur, but the patient should never know it happened. Before we talk about survival, we need to admit something harder. Even with the best design, sometimes pacemaker still fails. Not because someone did something wrong, but because hardware fails. Software glitches, a part wears out, or something in the environment interferes. And when it does fail, the risk is real. Unlike everyday electronics, a malfunction could cost someone their life. Imagine being the family whose relative died because of a device failure. How do you even process that? The fix, it's not a firmware patch, it's surgery. A replacement, carefully planned, yes. Minimally invasive, yes, but still surgery. That's why the design matters so much. Redundant power, segmented logic, early fault detection, subsystems that isolate faults and reroute control before anything escalates. Pacemakers don't survive by chance. They're engineered layer by layer to make failure invisible to the patient. In everyday devices, rebooting feels normal. It's the cost of flexibility. But when real lives depend on our code, the rules change. Recovery is still important, but prevention becomes everything. We're not just engineers anymore. We're designing for trust. Trust that the system will hold. Trust that faults won't ripple. Trust that when something breaks, the patient never feels it. We often call reboot a success, but maybe the absence of reboot is a deeper kind of success, quiet kind, because in systems where lives depend on timing, stability, and silence, sometimes the best system is the one that never calls for help. So when you design your next system, ask yourself, what happens when a reboot isn't safe?